So you will all recall that yesterday we began discussing a new ADT, the tree ADT, which is our first non-linear one. So it isn't like our list where we have a single order in which things can appear one after the other. Instead, we now have this parent-child relationship. We said that we can represent each element in our tree by a node, and we'll then have an edge between each node and representation. So if two elements have, or two nodes have that relationship of parent-child, we draw that line between them to represent that parent-child relationship. We discussed a few concepts, that of external nodes, those that don't have any children, those of internal nodes, which do have at least one child, and our special root node, which has no parent. We also talked about subtrees and defined two properties, the height and the depth of a node. We went over what the formulas for those are, or rather what the algorithms for those are, and looked at some examples for the tree given here. Then we talked about, well, what would the behavior of this ADT be? And we realized that as long as we keep a reference to our root and can be able to, given a particular node, return the parent or the children of that node, then we'll be able to go anywhere within our tree and be able to calculate things like depth and height that we had discussed before. We have some helper methods, we discussed those as well. All right, then if we used a linked structure for a concrete implementation of this, we realized that we could do this easily with the building blocks that we already have thus far. We just need to keep a few more references to be able to refer to a parent and a list of children. Then we looked at a few example applications and we moved on to binary trees. So now it's the exact same definition that we had for a tree. So it inherits all the properties that we discussed, all the behaviors that we have for a tree, except now we restrict the number of children to exactly two, right? Or rather, the maximum is two, and so we can have 0, 1, or 2 children. I believe this is where we left off. All right, we also mentioned that if we were to restrict it to 0 or exactly 2 children, then that would make it a proper tree rather than simply a binary tree. Now that we have just 2 children, we can actually uniquely refer to a single child, or rather we can refer to the children using an ordered pair and refer to the first and the last child uniquely, and we'll do that as the left and right child. Whereas with our general trees, we can have several children, and so we can't refer to uniquely some left child or some right child. All right, so you'll see continuing forward, we'll use those particular terms. We also said that alternative definition is this recursive one, that you could think of it as either a binary tree can either be a single node that has no children or a root node that has 2 binary trees rooted at its children. So each of its children are a binary tree. We then looked at a couple examples of this. I believe we were discussing, we discussed that of how we could use to store and calculate an arithmetic expression, how we could use this as a decision tree. Yes, and we should be here. So we understand that the binary tree ADT inherits all the behavior of the tree ADT, so it extends it if we were to implement it, and it would have some additional methods that now refer to these unique left and right children. So given a position, we can return if it has a left child and a right child. And so we'd also want to be able to check, does it indeed have a left child and a right child before actually calling those methods? So we now have the methods has left and has right. All right. I trust if there are any questions regarding what we've covered thus far, or as we are moving along, you'll put them in the chat so we can address them. Then there are some properties of a binary tree that we should know because we do use them at some points later, but I won't expect you to be able to derive most of them. There are a couple where we will discuss how these are derived. And in fact, the easiest of these will perhaps be number 4. You recall that yesterday I mentioned how if a tree simply has a root with a single child that has a single child that has a single child that has a single child, then our tree actually degenerates into a list. So perhaps let me just draw an example. So we have our root node. It has a single child, whether left or right. That has a single child. That has a single child. That has a single child. That has a single child, and so on for all n nodes. We actually end up with a list of length n, do we not? All right. And what would the height of this list be? All right. Still tree actually, though it has the same structure as list. So what would the height of this tree be? All right. I didn't explicitly or separately say it, though I did when we were asked the question that the height of it would simply be the height of the root. And we recall that if we have an external node, then its height is 0. For any other, the height is 1 plus the maximum height of any of its children. All right. So let's say we're counting. All right. So for this specific one, let's see, 1, 2, 3, 4, 5, 6, 7. Yes, that would be correct. Some say 8. All right, which is actually very interesting because this is the argument between n and n minus 1. So let's recall. The one at the bottom would have height 0, then 1, then 2, then 3, going, until our root has height n minus 1. All right. So it would be 7 for those that said 7. Those that said n, it should be n minus 1 because the very last one traversing, going down from the root all the way up to the last one would have a height of 0. And so this is really the maximum height that we can have for a tree. The maximum height would be if it degenerated into a list and we have this n minus 1 height. So that's where we get that from. The height is less than or equal to n minus 1. If we have any of these nodes now moved, let's say this one gets moved, and it becomes the other child for any of the other ones, then our height will be less. All right, it'll be less and less and less and less. The more and more we have nodes with more children, so 2 children rather than a single one. Okay, I saw a rather long question there. Let me move to our chat. Before writing semester test 1, because you at least treat any previous question paper, even if it's just on for the. All right, this was answered yesterday. I said yes, we will have time. We'll look at it next week Tuesday. All right. So yes, do please put in questions, but questions about what we're covering now, not ones that have been asked before, and certainly not ones that have nothing to do with what we're discussing now. So that's where we get that particular one. Some of the others are discussed in the text. Let's see, 2 is a rather simple one. We understand that the number of nodes that we have in our tree, if we use E to refer to the number of external nodes and I to refer to the number of internal nodes, is simply the sum of these two, because each node is either internal, has a child, or external, has no children. We can't have one that is both. And so the number of nodes that we have is simply equal to E plus I. Then if I was to use property 1, that E is equal to I plus 1 to substitute for E. So let me solve that first one for I. So if E is equal to I plus 1, then that means that I is equal to E minus 1. So if I then substitute that back into here, I get E plus E minus 1, which gives me property 2. All right. As for property 1, the text does go through that, and it's simply that if we have a tree and we start removing nodes in pairs, in a child-parent pair, we can always, if that parent had another child, simply move that child up to where the parent was. So it now becomes the child of its grandparent that had that parent as the child. Then we can remove them pairwise, and we'll put each one into some set of these are internal ones, these are external ones. As we move them in this fashion, we're always removing one external and one internal, the leaf and its parent. As we do this, we'll end up with a single node at the end, which will be an external node. And so that's how we have that the number of external nodes is simply equal to the internal nodes plus 1. All right, so it's more of a thought process where And you could actually apply to any tree. If we remove these pairwise, removing one external and one parent, we'll end up in the end with a single node that is an external node. So we'll end up with one more external than internal. Right. Some of the other ones, like number of external ones, we will take a look at that as it comes up in our discussions of trees, and also the log one comes up a lot, so we'll look at that as well. All right, so let us go through some of these properties. So we've already said that in our regular trees, we would have this node that is represented by some object that would store an element, it would store a reference to its parent, and then a reference to a list of some number of children. Now with our binary tree, we'd simply have to store an element or a reference to an element, a reference to our parent, and now just two references, because we know we'd have at most two children, and so we wouldn't need to use that reference to another list that can store several children. Now in this case, we can have two references, both of which can refer to a left and right child, or they can both be null, in which case we'll have an external node which will not have any children. And so now this node is what we can use to implement the position ADT for our binary tree. All right, what would that look like? Well, if we'd like to represent the tree that we have on the left there that has these 5 nodes, each of them would then be represented by this node structure that can store reference to an element, up to 2 children, and a parent. So we see that B is our special root node, so its parent reference is null. If we have an external node, for example, A, C, E, any of those will not have references to a left or right child. They'll simply store nothing there or a null in our particular implementation. Each of them has a reference to an element, right? The question was asked, would the node be like a header? But no, all our nodes do store a particular value. If it doesn't store a value, then it should be represented within our tree. And of course, if it isn't the root, then it will have a reference to a parent, as all the ones have there. All right, and then someone asked, so a binar, what is that referring to? Would you like to elaborate? All right, well, perhaps you type that in. I will go, oh, okay, that's fine. So binary, well, in what sense? In that it can, if we're referring to the number of children, yes, and exactly that. You can have up to 2 children, so binary, and that's how we say binary tree. Now, the only way, or rather, we do not have to use that representation. We do not have to use this node structure that links parents to children and children to parents to create our tree, to actually implement our tree. We could actually also use an array, and this would still work. We'd simply have to come up with some rule as to where the children of a particular node are stored so that we can refer to them just as we would in our node structure, and also be able to, from a child, be able to get to its parent. Because remember, we have to fulfill all those behaviors that you should be able to, given a tree, return the root, given a particular node, return the parent if it has one, return the left or right child if it has one, and for any for any non-root one, of course, return the parent. So we have to be able to implement those particular methods to have those behaviors of our ADT. So how do we do this? Well, there are actually two different, rather the approaches are the same, but the old text and the new text simply use two different calculations for this, but they are quite equivalent. The idea is that we'll always put the root at index 1. So whatever our root is going to be, we're going to store that index 1 in our particular array. Then to find out where the parent of, or rather where the child of any node will be stored or any element will be stored, we take whatever that rank of the parent was, we then multiply that by 2, that gives us the left child, we multiply it by 2 and add 1, that gives us the right child. So if our root is stored at 1, then what would be, or rather, where would our, let's start with the first one, where would our left child be stored? 2. Brilliant. Where would our right child be stored? Okay, again, it should be straightforward. It's simply 2 plus 1, which gives us 3. And we can try a few more examples so we prove this to ourselves. But for these two functions, if we put in different inputs, we'll get different outputs. So they should not, in fact, especially if you think of them as an ordered pair. For the same parent rank, we will get a different pair of left and right children ranks. So for parent with rank 1 for the root, where its left child to be stored would be 2, you got that correct. Where the right child would be stored would be 3. And we will not get any collisions. So let's look at our left child of our root. 2 is its rank. Where would its left and right child be stored? The left child is simply double the rank of this particular parent. That would give us 4. The right child is double plus 1. That would give us 5. Let's check then the right child of the root. Its rank was 3. So its child should be stored, its left child, at 6. That didn't intersect with any of the other two, the 4 or 5 of the left grandchildren. Then what about our right child of this child of rank 3? It will be double that plus 1, 7. So we won't get any collisions. So we can store this entire tree within an array. Granted, not all the spots will be used. We'll see that as we continue, we'll be skipping some particular ranks. However, we're able to store these at any place. Then, how would we get from any node to its parent? I keep saying node, I'm thinking of our node structure. How would we get to, there we go. How would we get from any element to its parent? We would simply do the reverse. Okay, and the reverse is actually easier than we think. It will be the floor of it will be divided by 2, the floor of the quotient, whatever that rank is, divided by 2. All right, so we'll ask, how do we get the rank of the root? Well, we set that to 1. That is what it is. All right, so let's say fine, we don't use our index 0 there because we're using ranks here. So 1 indexing, this is where we store our root. Okay, whatever particular element stores will be stored there. That's at 1. Its left child will be stored at, double that, 2. So this is the left child of the root. Let me say LCR. And then the other one would be double plus 1. So that would be 3. So this is the right child of the root. Then for each of these, so the left child of 2 would be stored at 4. So we have there the left child of 2. The right child will be 2 multiplied by 2 plus 1, 5. So that would be the right child of 2. We continue in this fashion. Some of them won't have children. We simply won't store anything at that particular rank. All right. Now, does it work? Can we? So this means great. Given any node, we can implement the behavior of left child and right child. And in fact, we can also check has left child, has right child by calculating the rank and checking if something is stored there. But can we do the parent part? Given a particular element, can we find out what its parent is? Well, let's look at these two. Both of these should have as their parent 2. So we simply take that rank, divide it by 2, and take the floor of that. As in, if it isn't a whole number, then we round down. So 4 divided by 2, that gives us 2. That's great. 5 divided by 2, that gives us 2.5. The floor of 2.5 is 2. So we can get the parent. So let's see, some questions. How do you get the rank of the root? Okay, we said that's always going to be 1. Does that mean we add from left to right? Well, you can calculate however you wish. Let's say we wanted to take 3 and store its left and right child, or retrieve its right child. I'd simply say 3 multiplied by 2 plus 1. That gives me what? 6 plus 1, 7. This is where the right child of 3 would be. All right, I want to go find what its left child is. Is it equivalent to truncating? Yes, it's the same as throwing away whatever comes after the decimal point. Zero is just null, well, we don't use it. So it'll be whatever the default type is. Because reference types, yes, it would store null. Equivalently, if we check at any child and we haven't stored something there because it doesn't have a child, then it will simply be a null, and we will infer from that that this node does not have a child. So we can implement our has left and has right. Does that make sense? All right, so if I ask you, where would the right child of 7 be stored? What rank will you give me? Yes, 2 multiplied by the rank of the parent plus 1. All right, then what if I ask you, 33, what is the parent of 33? What would the rank be of the element stored, of the element with rank 33? Exactly that. So you divide by 2, you end up with 16 and a half. We take the floor of that, we get 16. I could ask you then, who is the parent of that one? So who's the grandparent of 33? You'd have to calculate the parent of 16, 8. All right, good. So everybody who's given an answer understands. I hope that those who didn't do understand as well. If you don't, say so. We'll go over it again. The calculation is different than the text. It's still equivalent. You still end up with no collisions. And so within an array, without using a node structure, you can still store a tree and be able to actually do any of the behaviors that we talked about. All right, so a couple of questions to go over it again. Let's do that. So let me just erase all that. We agreed as a method of storing a tree with an array that we will use ranks, right? We even said that a rank is different to index. Index has that particular definition that we talked about, the number of elements that occur before it. Here, we're really just using it as a way to index into an array so that we know where to store a particular element. So we have our tree. Let's say this was our tree. It was storing just strings, let's say, right, or characters represented by these characters. I'm gonna write here, B, C, D, E. If I want to then store this in an array, then I can do that by calculating the ranks of each of these elements in my tree and storing that at the correct place within this array. We agree that the rank of the root will be 1. So I can store the root at 1. All right. How do you find the size? Well, our tree should have size. Oh, you're asking then, how would we find what the size of our tree is from the array representation of it? Well, that'll be linear time. We'd actually have to go through it and see which are non-empty ones. All right. Okay. But then all the other ones are constant time, so it's not that bad. So we have there A goes there. Where would B go? B is the left child of the root. Where would that go? You say, all right, to calculate the rank of a node, so I want to calculate the rank of B, I take the rank of its parent, okay, which in this case happens to be 1, and I multiply that by 2. That gives me 2, and so I know where to store this. And so actually when I want to call the method left child A, it should return to me B. So our left child A will say call rank A, multiply that by 2, and return whatever stored at that position in this array. That will then allow us to be able to retrieve B. All right, then for C, what would the rank of C be? We say that it's simply the rank of the parent, which again was 1, we put it there. Multiply that by 2 and add 1. That gives me 3. That's where I store C. All right, then D. Let me actually write the ranks as we're doing this. It's 1, 2, 3. So then what would the rank of D be? It should be its parent's rank multiplied by 2. That gives us 6. The rank of E, its parent's rank multiplied by 2 and add 1. That gives us 7. So I understand, okay, there's nothing at 4 there because there's no left child of B. There's nothing at 5 because there's no right child of B. At 6, I should return, I should actually store D there at 7. I should then store E. So now if I call has left B, I'll look there at 4 because I simply take the rank of B multiplied by 2. I find that there's a null there, right? So let me just remember that. So then I check that and I find there's nothing there. So I'll say no, B does not have left. I will then return false. All right, a question. Why do you want to use an array implementation? It seems arrays are less efficient implementation, in my opinion. Well, how about the fact that arrays already given to you, the intrinsic type in Java, and in fact, most programming languages, high-level programming languages. So you don't have to do anything. If we want to use that link structure, we have to create a tree node class. Then we create our tree class that sets up that link structure using the tree node class. So in terms of efficiency for the runtime of those methods, yes, certainly. But in terms of ease of implementation, then this one would win. And look, for each of our, even though they're both order n, the space used, all the arrays order big N because you have to know it beforehand, but the space used for each of these is simply the space necessary to store each of these elements. Whereas for our node structure, we have to store the element and 4 references. Those are the 2 children, sorry, no, 3 references will not be. Those of our 2 children and that of the parent. So I already said the element 1. So it's 4, it's the element, the parent, and the 2 children. Right, so even though the growth rate is the same, the actual amount of space used is more for our node structure. Right. Great. So I trust we're on the same page there. So we could actually store this in an array. We don't get collisions, so we're always able to store a child where it needs to be stored. We are able to find the left and right child given the rank of the parent. We are able to find the parent, as in find the rank and index into that, given the rank of a child, whether it be left or right. Using that floor calculation, we do get the correct one. Right. So here's an example of what that looked like. This is really all we did just now with a larger tree. Rank of A would then be 1, because that's our root. It's still going to be 2 and 3. Each of them, for the left child, you'd have double the rank of the parent. For the right child, you have double plus 1, the rank of the parent. So we see that on the left and right, and even that last one, for F, its rank is 5, its left child is 10, double that, and the right child is double plus 1, 11. All right, so we had discussed a couple of different traversals yesterday. I trust you remember. We talked about a pre-order traversal where you visit the node itself before you visit its children. For that one, we had to use a for loop for a general tree where we were actually, or we could use for each, as long as we're able to return an iterator over the children. Great. So for each child, we would visit it once we visited the parent. So for our binary tree, it's much the same, but simpler because we don't have to actually have this loop where we call pre-order and all the children. We know there are only 2 children. So we visit the parent first, or the current node, let's put it that way. And then if it has a left child, we will call this binary pre-order on that left child. If it has a right child, then we'll call that binary tree, that binary pre-order on that right child. Right. So much the same. Granted, looks like a little more code. In actuality, we're replacing our loop, whatever type we chose, with 2 conditional statements. If there's a right child, if there is a left child, call on that left child. If there's a right child, call on that right child. Remember, by convention, we assume that the order, or we take the order to be from left to right, so we'll work with the left child before we work with the right child. Then our post order, again, we did with the general tree, visit all the children. So actually recursively call post order on the children, then visit the current node. Now instead, we have our two conditionals. For our binary post order, we first call binary post order on the left child. That may call binary post order on its descendants, however many times, depending on the number of descendants, then visit that one. We do the exact same thing with the right child. Then after that, we visit the current node. All right, so still recursive algorithms for doing this, but now instead of loops, we simply have conditionals because we have a fixed amount of children, or rather a fixed maximum amount of children. Right. So we're going to look at that example that we had just discussed, that, okay, with a binary tree, we could also evaluate or calculate an arithmetic expression by using a particular traversal. We said that it would be a post-order traversal. And so for doing this, what we're going to do is simply recursively call this post-order traversal on the tree. When we visit an internal node, we're actually going to calculate, so use an operator on the values of the subtrees, the left and right subtrees. Of course, if it's an external node, then we're simply returning the value stored at that external node. We should recall internal nodes store operators, external nodes store operands or values. All right, so to calculate this, we're doing post order. So we only actually visit a particular node once we visited its descendants. So we're calling this on this tree, so it's actually called on the root. We don't visit the root first. We first visit its children, which means that we visit the left child first. Then, and let's actually number this to see how that post-order traversal would be done. The first one that I actually call visit on is the leftmost child of that. It is an external node, so it simply returns its value of 2. Then you call post-order traversal or binary post-order on the right child. That wants to visit this, but it has children, so it first recursively calls binary post-order on the left and right child of this particular node. Those are external, so that returns its value second, or it gets visited second. Then this one third. What that particular visit is, in this case, is if it's external, it returns the value. Now our first internal node is about to be actually visited. Because it's internal, it applies that operator to the two values at its left and right subchildren. So let's just write the order in which it's visited. That's the fourth one visited. It wants to take 5 minus 1. So it applies negation, that minus to, it's actually not negation, that's a unary one, but a subtraction to 5 and 1. That gives us 4. Okay, it's not the same one as that 4. Perhaps I'll put it in a circle to represent that that's the value there. Great. Now that parent can be visited, so it's visited fifth, and it executes that operator on the two values at its left and right subchildren. Those values are 2 multiplied by 4. That gives us 8. All right. So root was the first one that actually had that post-order traversal called on it. It has now completed, or rather, its left child has now returned with this value of 8. Then it doesn't visit itself. It first visits the right child after the left child. It now wants to visit this right child, but is an internal node. So it first calls post-order on its left then right child. So that was the fifth one. This is the sixth, and that is the seventh. Both of them simply return their values. There's a question, how did you get 8? Remember, the value that was returned by this one, my big arrow here, was 4. It's that 4 that I put in a circle. So now I can go to its parent, this one, and actually apply the operator. That dot is the same as multiplication. I'm applying that to 2 and 4, right? The values are, let me circle this, 2 and 4. Certainly 2 multiplied by 4 gives us 8. So the result of applying that operation of multiplication on 2 and 4 gives us 8. Now the left subtree of our root has a value. Now we're going to figure out the one of the right subtree. We said that the order that these are visited in is 6 and 7 for the left and right subtree of this right child of the root. We again apply this particular operator, multiplication to 3 and 2. We end up with 6. Put that in a circle to show that that is not the order of visitation. That is simply the answer. So I just put the 8 there because that was the 8th one to be visited. Now both children of the root have been visited. So the root gets visited last. It gets that 9. And what does it actually do? It says 8 plus 6, and that's straightforward. That will give us 14. All right, so I showed two things at once. The circles are actually what are the results of the visits at the internal nodes, but the numbers are what is the order of visitation for this type of traversal. If we're doing a pre-order traversal, the root will be visited first, and then each of its children. And those children will be visited before their children. All right, there's a request to look at that again. Let me just circle it so we understand. Those numbers that I've put above these leaves are not the values there. Those are the order of visitation. However, the values stored at these two external nodes are 3 and 2. The operator of their parent was multiplication. 3 multiplied by 2 gives us 6. So this is the actual value that is returned by that right subtree. We now have 8 and 6 as the values of the left and right subtree of the root. Well, what is the operation of the root? It's addition. Certainly 8 plus 6 will give us 14. All right, good. As long as we're on the same page at the end of it, that's all that matters. All right, so what would that look like? We're using a post order. So we understand that the actual calculation will only be done after the recursive call on the left and right child. However, here we have that base case that if it is an external, so if it has no children, then we should simply return the element stored at that particular node within our tree. Otherwise, if it has children, then call evaluate expression on the left child, call evaluate expression on the right child. This assumes that we're always talking about binary operators, so we always have a left and right child. If we were to work with unary operators as well, like negation, then, or what else? Exponentiation, whatever else, then we could add conditional statements that if there's a left child, call evaluate expression on the left child. If there's a right child, call evaluate expression on the right child. All right, but assuming we only use binary operators, we need 2 operands to do that. Question, so it's recursive? Yes. Remember, the traversals that we've looked at thus far are recursive, the pre-order and the post-order. So this is the exact same there. And we said that now with a binary tree, we don't have that loop where we call the method recursively on each of the children. Instead, we simply call it on the left child and the right child if they exist. In this example, we are applying binary operators, so operators that operate on 2 operands or 2 values. So we'll need that left and right child to do the operation. All right, so, and note that the order in which we do it is left child, operator, right child. So if we're doing something like subtraction that isn't commutative, then it has to be the left child minus the right child. All right, which is exactly what we followed. So if it's an operator, we'll then retrieve that operator after recursively calling evaluate expression on the left and right child, then actually evaluate it over there, and we return that particular value. That means that by the time we call this method on any parent, its children have returned some value, and we can validly be able to do this. So V starts as a root. Well, we could call this on any subtree, certainly, but yes, we are calling it on the entire tree, so V would be the root. Right, then as we recursively call it on the left and right children of V, we end up with, we're actually going down our tree. And so the V, that parameter, though initially the first argument was the root, it becomes the next child, the grandchild, and so on. All right, it's just the parameter, but we would usually pass as an argument the root first. Then we want to talk about a new traversal. We talked about a pre-order traversal and a post-order traversal. We will now want to talk about an in-order traversal. So for an in-order traversal, you visit first the left subtree. So you recursively call it on the left child, which will visit the entire left subtree. Then you visit the node itself. Then you visit the right subtree. Right? And an application would be to actually draw a binary tree. We could, if we want to draw a binary tree, then use this particular order to figure out where in the x-axis should our particular node be located. However, the y-axis will be determined by the depth of it, and that makes sense. Remember depth, our root node has a depth of 0. Then for any other one, its depth is 1 plus its parent's depth. So if we look at the y-axis horizontally, the root would be at the very top. Depending on how we envisage it, certainly would want it to go top down. But anyway, the root would have a depth of 0. Then the children of the root would have depth of 1, grandchildren depth of 2. It would work to actually have our tree give us the correct y coordinates. As for the x coordinates, we actually have to look at this root traversal. So let's look at that. So in order says to visit a node, and we start with the root, first visit its left child, then the node itself, then the right child. So to visit the root, it first visits its left child. To visit that left child, we first visit its left child. That's why that one gets the 1. Then we visit the node itself. That's why this blue one gets the 2. Then we visit the right child, and that's a recursive visit, so it's on the entire right subtree rooted at that child. So to visit 4, we first visit its left child. That is an external node, so we actually call visit on it. Then we visit that particular node, which is 4. Then we visit its right subchild. So all that was first visiting the left subtree, the subtree root at the left child of the root. After we visit that, and actually draw what we visited, then we visit the initial node itself, the root, and then we visit the right child. To visit this right child, we first visit its left child, then its right subchild, then its right child. All right. Note that we've actually gotten the correct coordinate for each of these along the x-axis. So let's say this is our x-axis. All right, the one that has a value of 1 in order traversal is the leftmost. That which appears second, if we're doing a movement from the left to the right of our tree, would be indeed the one that is visited second in our in order traversal. Then the one that should be third is third in our in order traversal, then fourth, then fifth, and so on. And so definitely this order, this traversal, gives us the correct order in terms of visitations from left to right. Granted, it doesn't give us the correct vertical one, but we said we can use depth for that. And let's actually look at what the depth is at each of the levels here. So depth of the root we agreed was 0. Depth of the children of the root would be 1. Depth of the grandchildren of the root would be 2, right? It's simply 1 plus the depth of its parent, which is 1 there. Depth of that fourth level would then be 3. So let's say you wanted to actually draw this using, Java. Either you want to really be lazy and spit it out into the terminal or the default output, or you actually want to use a GUI. Then we could use negative the depth, negative 0 simply 0, to make sure that it is correct top down, and use that in order traversal visitation order to print out the correct ones from left to right. All right, let me just put negation there so I understand that's negative the depth. Then some questions, just to be sure, how far will this method test go to the end of this particular chapter, or this lecture rather? Then, so all the numbers on the left are less than the root, and on the right are greater. Does this ever change? Yes, certainly it changes depending on the type of traverse that we're looking at. in an in-order traversal, yes, you're correct. The left subtree is visited before the root, then the right subtree is visited, simply because that's what we're agreeing on. All right, everybody's asking, will tomorrow's prac be based on? It. I actually have two pracs that are already set. The one is for a what do you call a raid list, and the other one is for a stack. It will probably be the raid list one. I do have to make some changes to that because all the methods or people that would have been asked are simply in your textbook, so you can't ask those. So the application may be a little more involved than usual, but it'll likely be the realist one, unless I can find something to kind of spice up the stack one. Right. And one doesn't mind if I ask the realist, obviously don't mind because you already have the code. All right, so we'll stop there since that is the end of the lecture. We're either going to continue and finish those last couple of slides tomorrow, or we can do them on Tuesday. Perhaps we'll do a little pre-prac vote on that. But then we've already agreed then at least one of those lecture periods, probably a bit more because we only have about 10 slides left, will be spent on looking at questions, application questions from the previous semester test, or rather from last year's semester test one. All right.